Please notice that we are officially starting with section 11.2, which is all about the parabola. So chapter 11 is analytic geometry, and we're going to talk about things called conic sections. And 11.1, there. Section 11.1 is just an intro to conic sections, and it wasn't really worth its own section as far as notes are concerned because I think in the book it's only like 1 or 2 pages. So we're just going to kind of introduce conic sections at the beginning of this section and then go from there. So you know how much we love a definition. So conic sections are the curves formed by the intersection of a plane and a double napped cone. You'll sometimes see it called a double naped cone, okay? So what in the world is this type of cone? Well, imagine a traffic cone standing like the typical way. And then imagine getting another cone, the same shape, the same size, and balancing it tip to tip. So you've got one right side up on the ground, you've got another one upside down, and you're trying to balance the two. That would be a double napped cone. And you can see it down here. We've got an image that shows what these cones are. Okay. So a double napped cone is a 3D shape formed by two congruent circular cones joined at their vertices, which is kind of what I explained with the right side up traffic cone and the upside down traffic cone resting on their tips. Depending on the angle of the plane, remember we're intersecting a plane with this cone. Depending on the angle of the plane, the resulting curve that you end up getting is a circle, an ellipse, a parabola, or a hyperbola. Okay. Now, James Wilson in the math department made a really, really cool video kind of showing how these conic sections, these are called conic sections. He made this really cool video showing how these conic sections are formed. I'm not going to show it here, but I have linked it and I really, really encourage you to go watch it. He has tons and tons of cool videos, but this one in particular is exactly what we need for this section here. Okay. So we have four images here. We've got the cones, the double napped cone, and then you can see this blue thing is the plane that is intersecting the cone. And depending on how that plane intersects the cone, you're going to get a very particular shape. So you kind of have to imagine seeing these from like a bird's eye view. So imagine looking down on these cones, like you're directly above the cone looking down, okay? If the plane is parallel to the base of the bottom cone, whoops, let me get the pen. So if the plane is parallel to the base, we end up with a circle. And again, the shape here looks kind of like an oval. This right here looks like an oval. So imagine looking at it directly from above. Imagine looking down on this with a bird's eye view, you would get a circle. Okay? Now, if the plane is at any random angle, you get what is called an ellipse, okay? And again, you have to kind of envision looking at these straight down, like you're standing above the cone looking down. What shape would that plane give you if it intersected the cone? Well, if the plane is intersecting the cone at some angle, you're going to get an ellipse, which is kind of like imagine a circle. So I wish I had an example, but like I have a cup right here. So imagine taking this cup, it's a plastic cup, and just kind of squeezing it. Okay. I don't want to do it too far because I've got water in there, but the mouth of the cup, that's kind of an ellipse. It's sort of just a squish circle. So imagine taking a plastic cup that's perfectly round and just sort of squeezing the sides in, and you get an ellipse. Now, if the plane that is intersecting the cone is perpendicular to the base, meaning it's going to intersect both cones, it's going to intersect the top part and the bottom part, what you end up with is a hyperbola. Now, these two little curves right here, they look very parabolic in nature, but they're not exactly. They're parabolic-ish, but they're not a parabola at all. It's something totally different. So if you were seeing this in like an XY plane, it would look kind of like this. So you have these two curves that are kind of uh, rear end to rear end. I don't know what you want to call it, but you have these two things, they're separated, but they kind of curve away from each other. Okay. And then finally, if you have this plane and it has to intersect the cone at a very specific angle, notice this side right here is parallel to this axis right here. Okay. When the plane intersects the cone in such a fashion, here is where you get the true, honest to goodness parabola. So please be very careful with a parabola and a hyperbola. They are very, very different. Okay. So we're going to focus in this video on the parabola, not this video, this worksheet on the parabola. Okay. So now what I want to do is the official topic one is just review from Math 171. Okay. So in Math 171, we talk a lot about quadratic equations. Okay. And we knew parabolas to be the shape of the curve for a quadratic equation. So it's the shape of the curve for a quadratic equation. And what you'll remember is we had curves like this. You can have a parabola that opens up. You can have a parabola that opens down. We could graph these generally kind of two different ways. We could plot points. Okay, we could just do the point plotting method, choose values for x, figure out what y is, go from there. Or you could use kind of like some really cool features of the parabola. So we could use what was called the vertex, we could use the x-intercepts, we could use the y-intercept, and then we could plot those specific points, which is kind of a play on point plotting, and we could get our parabola. Okay? So the equations that we dealt with in 171 came to us in two forms. We had vertex form of a quadratic equation, which is y equals a times x minus h quantity squared plus k. And then you would also see y equals ax squared plus bx plus c. So the first one in yellow was called vertex form. The second one was called standard form. They're the same, they could be the same equation. They're just different forms of the same thing. So you could take a standard form equation and write it in vertex form. You could take a vertex form equation and write it in standard form, okay? And they both are great. They have different features that we love. It's just two different forms of the same thing. Now, the vertex was a really important point for us. The vertex was the highest or lowest point on the parabola. So these two little parabolas I've drawn over here, the highest and lowest point, that's the vertex. And it just depends on if the parabola opens up or down. If a parabola opens up, it has a lowest point called a minimum. If it opens down, it has a highest point called a max. Okay, that's your vertex. And depending on the form your equation is in, we could get the vertex two different ways. So if we were in vertex form, the vertex was really, really easy to get. It was just the value that you're subtracting from x plus that constant k. Now, if you were in standard form, we had to do a little bit more work to get the vertex, but it was kind of not a big deal. You either did work to get the vertex or you did work to get the vertex form of the equation. So it was kind of the same amount of work either way. But if you were in standard form, right here, we had to do some work. We had to say, okay, we're going to let x, the x coordinate of our vertex, be negative b over 2a. You found out what x was. You plugged it back into the equation to get y, and those two values became the coordinates of your vertex. Okay? Now, in standard form or in vertex form, we had a value a, okay? And if a was positive, that told us that we had a parabola that was opening up. And if a was negative, we had a value, or we had a parabola that was opening down. Okay, so A was really important. It told us right off the bat, we could see really quickly if our parabola was going to open up or down. Okay, now you don't really talk about this next thing so much in 171, but you could have a situation where parabolas open right or left. So you could have a parabola that opens to the right, or you could have a parabola that opens to the left. And be careful, not a hyperbola, okay? It's two separate parabolas. They could just open to the left or to the right. And then if you have a situation like that, notice what your equation looks like. So let's do this in pink, all right? So if you did have a parabola that opens left or right, your equation was of the form y, or not y, woo! Your equation was of the form x equals a, and then in parentheses, you would have y minus k quantity squared plus h. Okay, so your x and your y values, they kind of flip-flop. Okay, so in this case, y becomes the independent variable and x becomes the dependent variable. Your vertex would be the same, you just have to be really careful and make note of what goes with your y and what goes off by itself in this case. Okay, so we, again, I don't, it's been a minute since I taught 171. I don't think you cover these right and left parabolas, but just know they exist. Okay, so that's kind of the overview. That's the introduction to the conic sections. I cannot recommend this video enough. It's just really, it's a nice, nice visual for how these shapes come about. And the way James has made the video, you can also get that like kind of bird's eye view that I was mentioning. So please watch that video and just take a brief moment and kind of remind yourself of some really important pieces of information about parabolas. There's one more thing I do want to mention really quick while I have you. There was also something called the axis of symmetry. It was kind of that invisible vertical line that went through the parabola and it went through the vertex. Okay, the axis of symmetry is called such a thing because if you were to take the parabola, let's say it was cut out on paper and you folded it along the axis of symmetry, the two sides would meet. Parabolas are definitely symmetric. Okay, so the axis of symmetry was always x equals whatever the value, let's say x equals, I don't want to say a actually. I'm just going to say x equals some number, which happens to be the x coordinate from your vertex. Okay, so take a moment, kind of remind yourself of quadratic equations, what they look like, kind of how they felt. Remind yourselves of opening up, opening down, how to get your vertex, axis of symmetry. It's you're not going to have to really do x-intercepts, but kind of think about x-intercepts and y-intercepts. So just take a little trip down memory lane really quick, and then we'll come back and we'll talk about a deeper level of the parabola.